Welcome to this course on C++ templates, and in this video I'll be going deeper into how to create and use C++ template functions and classes in your code. The course is designed for beginning to intermediate C++ programmers. I'm assuming that you have at least 6 months solid experience of coding in C++. Experience of C++11 will be useful but isn't essential. And I'm assuming that you have a reasonable understanding of the basic use of function and class templates. If you've taken the previous course in this series, Introduction to C++ Templates, then you will be well prepared. The course starts by showing how to make templates more flexible by using non-type parameters and defaults. I then discuss overloading and specialization, which let you create custom versions of templates for particular combinations of types and values for those cases where the base template won't do. You'll need to use template parameters when a type parameter is itself a template type. You'll meet this quite often. Although the syntax can be daunting, it isn't really difficult. I'll then discuss practical use of templates, including how they work with inheritance and when you might want to force instantiation. And after reviewing the importance of templates in modern C++, the final part of the course looks at 3 advanced techniques that are widely used today: generic programming, type traits, and policy-based design. I'll explain what these are and show how to use them. By the end of the course, you'll be able to use non-type and default parameters and be able to overload and specialize template classes and functions. You'll also understand how important templates are in modern C++ and how generic programming differs from OO programming. You'll also be able to use features such as type traits and policy-based design to create robust and practical modern C++ code. It's possible that you may want to have template parameters that are not types but values. Such parameters are called non-type template parameters. Let's consider the case of a simple template stack class. I have a version here that dynamically allocates memory using a constructor parameter to specify the size. You can see how memory is allocated in the constructor and freed in the destructor. But suppose I want to use an array to store data instead of dynamically allocated memory. This would be useful if you wanted to avoid the overhead of allocation at runtime, but it raises the question of how to provide the array dimension to the compiler. Here's how I do this for stack. I've now got a second template parameter, which is an int. This defines the size that I want the array to be. The fact that I put int instead of type name shows that I'm expecting an integer value rather than a type name. And you can see this is used to size an array. And you can also see how this has to be used if we define members of the template class outside the class itself. Let's just see how we could create a couple of instances. Here I have a stack of int size 20 and another stack of int size 10. Now, an important thing to note here is that each instantiation creates a new type. S10 is a completely different type to S20 because they contain different size arrays. This can lead to an increase in the size of the generated code if you use a lot of different values. We can see this by looking at the generated code. nm is a Unix utility that lists the symbols in an executable. Running this on the binary shows that there seem to be 2 distinct stack types. We can see that there are 2 distinct stack types, one of which contains 10 and the other one of which contains 20. The names, however, aren't very friendly. Let's just take a look at a couple of them and see what they mean. I'll copy that. There's a utility called C++Filt, which can be used to demangle names and make them more intelligible. And sure enough, we can see that this represents a stack of int size 10. And if I go and look at the one with 20 in it, as you might expect, that represents a stack of int of size 20. Now, it's important to note that these are completely separate types. There are no implicit or explicit conversions between them. There are a few restrictions on non-type template parameters. Generally speaking, they can be constant integer values, enumeration values, L-value references, or pointers to objects with external linkage. They cannot, for example, be floating point values. C++17 allows the use of auto for non-type template parameters. For example, template auto n. Then x of 3 will deduce n to be int, x of a character will deduce it to be char, but x 2.5 would fail because floating point types can't be used. We know that you can specify defaults for function arguments, so why not for template type parameters? And it turns out that, of course, you can. Continuing with the stack example, I can provide defaults for either or both of the parameters, and that's exactly what I've done here. The type name has been defaulted to int, and the size has been defaulted to 10. These are used exactly as you'd expect. Here we can see 3 examples. In the first one, I've provided both parameters. The second one, I've taken a default for the size. And in the last one, I've taken defaults for both. The rules for default template parameters are same as for functions. Once you've used a default, you need to accept default values for all the ones that follow. In the last example, note that you do need the empty angle brackets. This is because stack is a template type and it needs the angle brackets for type parameters. The fact that I'm using 2 defaults doesn't change this. Using default template parameters is a very common technique. For example, in the STL, you usually instantiate containers with 1 type parameter, which is the type of the contained value. But the definition actually takes 2 type parameters, one of which is defaulted. And since it's uncommon to provide your own allocator for STL containers, giving a default for this is pretty sensible. And we can see this if we have a look at the definition of vector. So here it is on CPP reference, and you can see that vector is a template class that takes a type parameter t and an allocator which defaults to the standard allocator. This almost always defaults to the standard allocator, and many people don't even realize that there is a second parameter. You, of course, need to decide whether you want to do this. In the case of an STL container, the standard allocator is a good choice, but in my stack, is 10 a good default size for a stack? It certainly isn't intuitive, so it may be better to require the programmer to provide it. You know that it is possible to overload ordinary functions, and you'll find that the same is true of template functions. The rules can be slightly different. You've seen that templates use the same code with different type parameters. Here I've got a simple max template function, which I instantiate with int and double arguments, but as usual, it uses the same code in the body. What if I want to find the maximum of 3 values? Well, I could do it like this. Here is an overload of max taking 3 parameters and with a slightly different body. Supposing I used max with a pointer type, then it will compare the addresses in the pointer variables, which probably isn't what I want. What I want to do is compare the values that the pointers refer to. So I could define an overload that will work for pointer types. So you can see that I'm now dealing with t stars rather than t, and that I compare the values that the 2 pointers refer to, and then return whichever of the pointers refers to the greater value. There's something to note here. Template resolution is very particular about types. My overload needs a const pointer, and if you pass it a non-const pointer, then it won't use this overload, but instead will use the plain template. You can easily verify that for yourself. While this works fine for many pointers, it obviously isn't suitable for C-style strings because I need to use string compare. So I can provide an explicit implementation for const char star, which does what I want. Here I've got a version of max with const char star as the type, and you'll notice that it is not a template function because it doesn't have any template parameters. The compiler will normally prefer the non-template version if one is available rather than instantiating a template. So in this case, it will prefer my const char star overload rather than instantiating the template. Well, let's see how these work by adding some test code in. And you can see I'm testing the maximum of 3 values, I'm comparing some values through 2 pointers, and I've also got some character strings. Let's build this and see how it runs. And you'll see, comparing the 3 values, the maximum is 7, which it should be. When I compare the 2 pointers, it's using the pointer template, and the maximum of 4 and 5 is indeed 5. When I test char stars, it's using the string template. I have ABCD and ABC, and it tells me that ABCD comes out as the greater, which is just what it should be. Before finishing this section, let me mention a couple of other points that are relevant to overloading template functions. The first concerns how the compiler decides which template to use when it has a choice. For example, consider these 2 functions. I have 2 overloads of a function f. The first one takes t, while the second one takes a pointer to a t. Let's try using these. In the first case, I'll call f with an int, and in the second case, I'll call f with an int star. And if I run this, you can see that I get the result that I'd expect. The first call calls the first overload. The second call with the pointer calls the second overload. But this is slightly more unusual than you might expect. If you think about it, either of the overloads could match this second call. With t being int star, it would call the first overload, but if t was int, it could call the second overload. Now we know that compilers tend to complain if they find any ambiguity, but in this case, it obviously does not find any. It turns out that when dealing with generated template functions, the compiler will choose the one that it considers to be more specialized, and in this case, that is the pointer version. The rules are rather complex, but if you're interested in the details, you can find a discussion in the C++ templates book by Van der Voort and Jasutis. The second fact that you might need to be aware of is that type conversion is not used with template parameters. Let me switch back to other projects. What I'm going to do here is add an overload of max that just works with ints. And of course, this isn't a template function, just a plain ordinary function. And then let me add some code in here that calls max, but it does it with mixed parameters in one double and one int. So what's it going to do? Well, let's build this. And you'll notice that I do get a warning about an implicit conversion, which gives you a hint as to what's going on. And if I run it, it shows that it's used the int version. Conversion is not applied when using templates. The compiler cannot find a template version that matches a double and an int, but it can do a conversion in order to use the int version. So that's what it does. You've seen that you can overload template functions in order to provide specific implementations for particular types. In the same way, you may want to provide a version of a template class for a particular set of parameter types. This is called specialization. You might want to do this, for example, because if a template class uses numeric types, you might want to take advantage of the fact that for integers you can multiply and divide using shift operations rather than the usual arithmetic operations. So let's start looking at this by considering a template class that takes a single type parameter, such as our now familiar stack. Supposing I want to provide a version of stack for use with standard strings. Well, I could do it like this. Here we see a version of stack that is specialized on string. You notice that I still need to provide the template line, but the angle brackets are empty because there are no type parameters. The type being used for specialization is placed after the class name in angle brackets. Usually, you will define members inside the class body, as you can see here, where I've defined push. Notice now, of course, that we've got strings in here rather than any type parameters. If you want to define members outside the class body, then you have to do something that looks like this. Here is top implemented outside the class body. And note how you need to define it as an ordinary function, not a template function. We still have to provide the type after the class name in angle brackets, but we don't have a template line before it. Now, another interesting thing is you don't necessarily have to specialize an entire class, but you can choose to specialize individual member functions, leaving others in their generic form. Here's a simple version. I have specialized the top function just for integers. Notice here that, unlike the definition of members for a full specialization, in this case you still need to put in the template line because this is a template function. If I now add some code in here, I can create a stack of strings. Now I've created a stack of ints and I'm calling top. So let's just compile this and see what happens when we run it. You'll notice that it's creating a stack of standard string, which is the comment that I put in the constructor. So it is using my specialized version. And you can see that when I create a stack of ints, it's using my int pop specialization as well. If you have more than one type parameter, you may choose not to fix all of them. This is called partial specialization. Let's investigate this by considering a simple template class with two type parameters. This class represents a two-tuple or pair, often used to represent key-value pairs in maps or dictionaries. And here we can see pair, which has two members of type T and U. It has constructors, and it has some getters to return you those two members. And you use it down here just as you'd expect. I want a pair of int and double, and if I run the code, we can see that it does indeed retrieve me the two members, and that's exactly what I want. But supposing that I want a specialization where the key is always going to be a string, well, I could do it like this. This is a specialization where the first type has been specified as a standard string. So I now only have to give one type name, but I do have to tell the compiler that the other type is a string. And as you can see, I do this by putting the type parameters after the class name. And so this is going to be used if I create a pair whose first type is a string. Let me go and add some code in here. A pair called K, whose first type is a string. And let's have a look at what happens. Let's build that. Now let's run it. And you can see that it says it's using the specialization here, which is what I'd expect. There are several other ways that we might want to use specialization. For example, you might want both template parameters to be the same type, and we could do it like this. Here is a specialization where I've only got one template parameter, but the pair is using T in both cases. Finally, I could also specialize it for the case where one or more parameters is a pointer. So I could see something like this. And again, here we see that I've got two template types, the first one of which is a pointer. And that would be used if, for example, I created a variable of type pair, int star, and double. As you might expect, if more than one specialization could match, then the compiler is going to complain about ambiguity. Template functions can be specialized in the same way as template classes, but instantiation can be complicated by overloading an argument deduction. Full specialization uses the same syntax with empty angle brackets, but in this case, the compiler can use the arguments to the functions to determine template parameter types. Let's see how this works using our trusty max function. Here, I've added two specializations, one for int and one for int star. And it's easy to demonstrate that the right specialization will be called by adding some code to main. Here I'm calling it with a pair of doubles, a pair of ints, and a pair of int stars. So let's build this and see what the result is. And as you can see, the doubles use the base template, the ints use the int specialization, and the pointers use the int star specialization. One thing to be aware of here is that specialization of function templates don't take part in overload resolution. Only base templates are considered. And as a final thought, I'll note that for historical reasons, function templates can't be partially specialized, although you can get a very similar effect with overloading. The way in which templates are processed means that they will be instantiated as necessary. But sometimes you might want to force instantiation of a template, and this is called explicit instantiation. You can do this for both function and class templates using what is called an explicit instantiation directive. So let's start with our two examples, the max template function, which you can see here, and the stack template class. I can force an instantiation of the max function like this. And here you can see an instantiation of max for double. You can see as well that it consists of the keyword template followed by the entity that you want to instantiate. And of course, specifying the type here tells the compiler exactly what it needs to do at this point. In the same way, I can force an instantiation of stack. Here I'm telling the compiler to create a stack of int at this point. Let's build the code. Just notice that I'm not using these things that I've instantiated anywhere in the code so far. If I switch to terminal and I run nm on the binary that I've just built, we can see all the symbols. And if I look back up towards the top somewhere, we can see something that looks pretty much like max. And if I now run the CppFilt utility to demangle the name, we can see that it is indeed a version of max for double. Again, looking back up here, there are quite a lot of entries for stack. Just picking one of these and running CppFilt on it again, you can see that it is indeed a member of the stack of int, showing that they have been built. You don't have to instantiate a whole class if you don't want. You can instantiate individual members like this. Here, I've just instantiated the pop member for a stack of doubles, leaving the rest of the class generic. Obviously, you can't instantiate member functions for a template class that has already been instantiated because all those functions have already been created. Why might you want to do this? One reason is to reduce compile times. If you know that, say, stack of int is going to be used a lot in your code, you can instantiate it in one translation unit and then refer to it using extern in others. Let's have a look at that. I've created stack of int here, and if I go to another file, here I've declared that stack of int as extern, and I can then use it in the function, and the link will pick it up like a normal extern variable. And finally, a second use for this could be when creating libraries using template types, because a template definition that hasn't been instantiated at all won't be included in the final build because the link thinks that it isn't used. And so by using explicit instantiation, we can make sure that it will be included. Sometimes a template parameter itself has to be a class template, making it into what is called a template parameter. I can demonstrate this using the stack class. Up to now, I've used an array to hold the data inside the stack, but I might want to choose another type, such as a vector or list, and I might want to do that when I create the stack. Doing that might look something like this. Here, I'm specifying the type to be stored in the stack, int, and the container used to implement it. I'm using a made-up container called myVector because using a standard vector adds a bit of complication, which I'll explain shortly. You can see that we end up with nested templates. Before C++11, you had to put a space between the two final angle brackets, otherwise you'd get a compiler error. This was because the way that the parser read the code meant that it took the angle brackets as a right shift operator, which really confused it. That has since been fixed, but you will still see code that uses a space, and that's often because that's how people learn to write it. Now this looks a little bit ugly because I have to specify the contain type twice, and there's a slight chance that I could get that wrong. If I used a template parameter, it would let me write it like this. Now I've only got int and myVector, and the compiler will assume it's a myVector of int. This makes using the class simpler and avoids the possibility of type errors. How would I define the stack in order to use this? In this example, T is the normal type name parameter, and C is declared as template type name. This tells the compiler that C is a template type with a single type parameter. If it took two type parameters, then I would say template type name, type name. One thing to note here is that you can only use class when you're doing this. You cannot use type name. And I could, of course, put a default container in here as well. I could say equals myVector. Now I could use one of these and get myVector as the default type and only have to specify int. Let's take a minute at this point to walk through a real implementation that uses an STL container with standard vector as the default. The first thing you'll note is that the code is much simpler and shorter. Containers such as vector and list are resizable, so I no longer need the size or to check for overflow. The standard container operations, pushback, popback, and back, will deal with managing the stack, and I only need to check for underflow. The only complicated things here are the initial template line and the way in which the data member is defined. In the initial template line, the second type parameter is the container, and STL containers have two type parameters, the contained type and the allocator. So I need to tell the compiler this by saying template type name, type name. This means that I will also need two parameters when I declare the data type down here. The first will be T, the type that I want to store in the stack, and the second is the memory allocator, and I can use the standard allocator for this. This allocator is also a template type, so I have to pass T in as its type parameter. I can use this in the same way as any of the previous versions of the stack, as you can see here. Inheritance works pretty much the same for template classes as it does for non-template classes. There is nothing significantly different between the template and non-template cases. Let's start with a simple template array class, as you can see here. If I wanted to add some extra functionality to array, I could inherit from it in the normal way. I've got a type called newArray that inherits from array of T. NewArray has to be declared as a template type because the base class needs a type parameter. So you'd use it in the way you'd expect, providing the type in angle brackets. Here I've got a new array of int so that the type can be provided to the base class. However, supposing I just wanted an array of ints, then I could do it like this. Now I'm inheriting from a specialization of array. That means that intArray itself is not a template class, since it has been fully specified at this point and has a default size of 10. However, if I wanted to allow the size to change, but not the type, then I could do something like this. This turns intArray2 back into a template type because of the need to provide a non-template type parameter. I could do something similar if I wanted to fix the size, but allow the contain type to change. There is, however, an important subtlety due to the fact that the compiler may not know types at compile time. Building inheritance trees often involves protected members, and templates can complicate accessing protected members from derived classes. Let's investigate this. I'll start by defining a simple pair of classes, base and derived, and you can see that base has a single protected member, so it will be accessible to derived. Now, supposing that I change base to be templated. The protected member is now of type T. Can derived still work with it? And it turns out that it works fine, provided that derived is not itself a template class. Here, derived inherits from a specialization of base, and so is not a template. However, if derived is itself a template class, then you'll find that it can't access the protected member. Let's change that. Now you can see that derived is itself a template type. I can now say I want to have a derived of int in there. And if I try building it, sure enough, it says use of undeclared identifier prot. It cannot access the protected member. Now I'll show you how to fix this first, and then I'll explain why it happens. And it turns out that there are 3 ways to get around the problem. The first is to use scope resolution. I can tell it that prot is a member of base, and if I build this, it now builds fine and it runs correctly, giving me the default value of 0. So that's the first way of doing it. The second is to use using to bring the name in from base. Let me copy that. Here I will say using, and that does exactly the same thing because the compiler now knows that when I say prot, I mean base T's. And I build that, and that builds exactly the same again. The third, and perhaps easiest way, if I just get rid of that line, is to use this. Now, if I build it, again, works fine. So, 3 equivalent ways. Why is that? The types of type parameters and the values of non-type parameters, of course, aren't known at the time the template is defined, but what some constructs mean may depend on those types and values. This leads us to the idea of dependent and non-dependent names. The rules around how these work are very complex, so I'll just present a brief summary here. Things that are non-dependent names, things that can be looked up and bound when the template is defined, and this tends to hold even if there might be a better match when it was instantiated. When something is dependent, on the other hand, lookup is postponed until instantiation time and uses different rules. One of these is that unqualified names do not automatically get resolved to members of a base class when we are talking about dependent types. And as a result, you need to qualify it using any of the 3 techniques that I showed. Templates are an essential part of modern C++, and it is not an exaggeration to say that modern C++ programming style is built on them. I'll briefly mention 4 examples that you'll encounter in modern C++ code, and which exemplify how important and fundamental templates are. These 4 are the CRTP idiom, the STL, smart pointers, and function objects. CRTP, the curiously recurring template pattern, is an idiom that was first recognized by Jim Coplian. A derived class inherits from a template base class, but the type parameter for the base is the derived class itself. One common use of CRTP is to avoid the overhead of virtual functions because it enables static polymorphism. Here's an example. I have a template base type, and the derived class name becomes known to the base class through being used as a type parameter. The derived class is substituted for T in the static cast when the class is instantiated, and that enables the this pointer to be cast to the derived type, which means that the call to the function doesn't have to be virtual. The standard template library provides a set of containers, iterators, and algorithms that use many template techniques to implement efficient and generic data structures. The containers are templated classes, while many of the algorithms use template functions. We've already seen examples of STL containers in use in this video, so I won't take this any further now. Smart pointers are used to manage objects, overloading the arrow operator to provide indirect access via a pointer-like object. The use of template classes means that generic smart pointers can be used to manage a wide range of different types of objects. The standard library now provides several types of smart pointer. In particular, unique pointer and shared pointer which are very widely used. Here we see an example, a simple class foo that contains a single data value. An instance is passed to a unique pointer, which gives access to foo's members through the arrow operator, and which also deletes the instance when the unique pointer goes out of scope. Finally, function objects. If you want to pass a function as an argument, you have several options. We have function pointers, classes that overload the round brackets operator so that an object can be used as if it was a function. And now we've got lambdas. How could we unify these so that we could use any of them? Well, C++11 introduced the standard function type, which represents anything that can be called like a function, and it uses templates to specify the arguments and return type of the function that it represents. Here's a simple example. I've got a function called square that takes an integer and returns one, and a function object, which, as you can see, takes an integer and returns one. This means that it can be used to invoke square because the signatures match. And you also see that I have a lambda here with the same signature, so I can use the function objects to call that as well. I'm now going to introduce you to generic programming, a very important topic in modern C++, one that is firmly based on templates. As you'll see very shortly, this introduces a third way of programming to C++, which sits alongside and has a status equal to the procedural and OO styles of programming that you're familiar with. I'll introduce the idea through an example. It's important to understand the ideas behind generic programming because you'll frequently meet it in modern code and especially in the standard library. Consider a function, like the one we have here, that tells you whether a string contains a given character. Notice I'm using pointers, and I'm moving the pointers around using ++, and I'm using pointer comparisons. And although using raw pointers may seem old-fashioned, I'm using C-style strings and pointers here for a reason, which will become apparent very shortly. There are several ways in which this function is not generic. The first is that it relies on null-terminated strings and will always search to the end. And that means you can't search part of a string. Let's fix that. Here is a version that takes pointers to the start and the end of the range that I want to search. What I need to do now is provide an end. There's the end, it's the address of the string plus the size of the string. And then, of course, what I need to do here is I need to add the extra argument. And let's see how this works. If I run it, it returns me, it found the comma, and I print out the string from there on. This is an improvement that I can now search part of a string, but it's still not generic enough for us. Reason being, of course, it only works with characters. So an obvious thing to do would be to make this into a template. So let's do that. Here is a template version. You can see that I take a character of type T and I take pointers of type T star. And apart from that, the code is pretty much the same. And indeed, if I build that and I run it, it runs exactly the same as before. What's interesting about this is that because I'm using a template, I'm not limited to characters. And so in here, I could say, let me try creating an array of ints, calculate the end position, that array of ints, and then can I find the number 4 in that array of ints? Let me build this. Indeed, it does find 4, which is what I'd expect. This is great, but it's still not as generic as it could be because there's one more restriction. I wonder if you've already spotted it. The restriction is that the start and end have to be pointers. That limits how it can be used. What could we do to change that? Let me make a change. This might seem a simple change. I've just introduced a second type parameter that I've called iterator, and you'll notice that the start and end are now iterators and the return type is an iterator. If I now build this and I run it, it runs exactly the same as before, and that's great. This might seem simple, but it actually is a profound and rather subtle change. Because if we ask ourselves, what actually is iterator? It isn't a type, it's not a class or an interface. And in fact, iterator is a concept. It's a name for something that has the properties needed by an iterator. And in this case, that involves supporting comparison using not equals, increment using ++, and dereference using star. The really interesting fact is that anything can be used as an iterator as long as it supports those three operations. And that means that we can use traditional pointers, or we could use a class that overloads those operators. That lets us define a function whose parameters can be traditional pointers or objects, and that's something that we hadn't been able to do previously. So we can use the same function to work with both specialized iterator objects and pointers into traditional arrays. As a final note, C++ has been trying to formalize this idea of concepts and bring them into the language for some years. This will give developers a way to specify the properties that a type must have in order to be acceptable, and if nothing else, it will make for better error messages when something isn't suitable. One problem you'll encounter frequently when using templates is that only certain types may be valid for use with a template. For example, you wouldn't want someone to try using a string with a template that is designed for use with numeric types. You may well get compiler errors if you use an incompatible type, but these are often unhelpful and sometimes incomprehensible, and it will be good to have a better way to check type compatibility. Type traits are a way to get information about types so that you can make decisions based on type capabilities. Here's a simple example. Supposing that we want to check that a type parameter is a character type. The idea is simple. I start with a struct that has a single Boolean value, which by default is initialized to false. I can then provide specializations. And you can see that I have one specialization for char and a second specialization for wchar_t. And that means that the value member for character types will be true, but for anything that isn't a character, it will be false. Let's see how we might be able to use that. Here's a very simple function which checks the type parameter. So you can see here that I have a template function, takes a type t, and it goes and uses my isChar struct to decide whether t is a character or not. Let me have a go at using this in main and see what we get. There we are. I can call foo with a character and foo with an integer. If I build it, then it builds. And if I run it, it says that char is okay, but the second call is not a char. So I've managed to tell what t is. Although it's quite possible to define your own traits like I just have, C++11 has defined the type traits header that contains a number of useful traits which you can use to check types and capabilities. Let's take a look and see what's on offer. Here it is at CPP reference, and we can see we've got the header type traits. Let me just pick out a few of the most useful. You can check for numeric types using isIntegral and isFloating_point. Looking down, isPointer may be useful for checking whether a type is a pointer, and we've got other traits such as isArray and isEnum, isClass that let you find out a lot more about types. Now, you often need to construct objects in template code. You can see we have a whole load of traits here. IsConstructible, isDefault constructible, isCopy constructible. They let you find out what sorts of construction a type supports. You can use these in code exactly the same way that I did my handmade one. Let's go back. Let's add a test for an integral type. First of all, I need to include the headers that I'm going to use here. I've included the type traits header, and I'm also going to use assertions. Down here, I can add a class that is going to use this. Here is a little class called test, takes a parameter t, and what I'm doing is in the constructor, I'm asserting that t is an integer type. Let me go try at using this. I'm going to try creating tests that uses int, and I'm going to try creating another test that uses double. Let me build this. It builds, and sure enough, when I run it, I see that an assertion failed, and that tells me that in the second case, I didn't have an integral type. Ideally, of course, you'd want to perform these checks at compile time rather than run the risk of runtime failures. C++ has added a feature called static assertions that let you do this. Policy-based design, also known as policy-based programming, is a C++ idiom that was first popularized by Andrei Alexandrescu in his book, Modern C++ Design. This idiom uses inheritance, often multiple, from template base classes. It allows users to plug policies, or in other words, strategies, into a host class to get a combination of behaviors they want, and can be regarded as a compile-time version of strategy. One of the main advantages of this idiom is that it helps prevent a proliferation of custom classes while allowing easy extension through the definition of new behaviors. Let's consider an example. Supposing I have a class that manipulates data. Sometimes I want access to be thread safe, but at other times I don't, and I don't want the overhead of locking when I don't need it. There are a number of ways I could do this. For example, I could create two different classes, or I could pass a flag into the constructor and check it. But policy-based design gives me an alternative. I'll start by defining a base class that defines virtual lock and unlock methods. These form the policy. So here you see a class called locking policy with two virtual functions. I can now define two derived classes which implement the behavior I want. I have one called lock, which implements the lock and unlock functions, and another called no lock, which doesn't implement them. Using these, I can either lock or not lock. And let's see how we do that by adding a client class that's going to use it. Here is a simple client called data. You'll notice that it inherits from locking, which is a type parameter. That means that the compiler has no idea what functionality it might have. And you'll notice that I have to use this to reference the lock and unlock members because names from a dependent base class are not automatically in scope. So let's try using this. See that I create a couple of dynamically allocated integers, and here I create two instances of data to work with these integers, one of which uses lock and the other of which uses no lock. We'll see when we execute the code what happens when we execute the do something method. So let's build this and run it. And you can see that when we use our first instance, which did locking, we see locking using the data and unlocking. The second instance, which used no lock, there is no sign of locking being used. And what's interesting here is when using no lock, there's no implementation. And because these empty functions are inline, they'll disappear when the code is built, thus making everything very efficient. Let's add a second policy. Our instances use a pointer. So should they call delete on it at the end of life or not? Sometimes we might want to, other times not. So that seems like a good candidate for a policy. Let's add deletion policy. Here I have a type called deletion policy that has a single virtual function called deleter that takes a pointer to an object that it's going to delete. And of course, this has to be a template class itself because we don't know the type that we're going to delete yet. Now I can add a couple of implementations of this. Delete is implemented so that its deleter function deletes the object. No delete implements deleter as a no op. I can now rewrite my client class to use this. And you'll notice now that I have three type parameters, T, my locking policy, and my deletion policy. Because the deletion policy class is itself a template, that makes this a template parameter. And you'll notice, again, I can easily call this by putting in a destructor and calling deleter from in the destructor. Once again, I have to use this because the name is not going to resolve automatically. In order to test this, I need to go down and add the other parameter to my declarations here. I'll call no delete for the first one, and I'll use delete on the second one. Let me build. And when I run it, you can see that first instance locks and unlocks, but doesn't mention deleting, while the second instance just uses the data but doesn't lock, and it deletes it. And of course, because of the wonders of inlining, this code is going to be very efficient. Here are some exercises so that you can put what you've learned into practice. Take the pair class that you met when we discussed partial specialization and complete it by adding other useful operations, such as the equals equals operator. Now create a simple associative array class that manages a collection of key value pairs. This will be a simple version of the map or dictionary classes that you find in every set of collection classes. You can use your pair class to hold the key value pairs and assume that entries are immutable. Use a suitable STL container to hold your collection of entries. Implement the following operations. Add, which will add a new key value pair and fail if the key already exists. Get, which will return the value for a given key, failing if there is no such key. And get or else, which returns the value for a key or a default if there is no such key. You should also implement operator square brackets as an alternative to get, and also add any other functionality that you think might be useful. Finally, implement a policy-based logger class. This should support at least two policies, the first of which determines the destination for the log messages, for example, writing to standard output or acting as a null logger and not writing anything. A second of which determines whether a timestamp will be added to log messages or not. And if you can think of any more useful policies for this class, add them as well. Let's look at what we've covered. We started by examining more of the mechanics of template creation and use, including overloading, specialization, and the use of template parameters. We then moved on to topics concerned with using templates in practice, such as explicit instantiation and their use in inheritance. We finished by considering the importance of templates in modern C++ and looked at modern template-based coding techniques such as generic programming and policy-based design. Where do you go from here? Reading both written material and posts on the web will expand your knowledge, and reading code is also an excellent way to improve your understanding of templates. It's crucial to experiment by writing code to test out your understanding of what we've discussed. You may also wish to watch the third and last video in this series, which will introduce you to some advanced features that were introduced in the C++ 11 and 14 releases. So it just remains for me to say that I hope you've enjoyed our brief exploration of C++ templates and to thank you for watching.